We have floating panel. All right, let's start. So good afternoon, everyone. Hope everybody has enjoyed a great spring break. Just reminder, we have some homework deadline today, I guess. Like I would say a lot of students have already submitted homework assignments, but if you do want some extension, I will need to look at like near the deadline, like near late night tonight, and see if how many of you are requesting for extension. If not many, I guess we have to maintain the same deadline. Otherwise, we'll consider have 2 more days, like on Thursday. Meanwhile, we'll have a released homework 3. The workload is quite light. There's even not any programming assignments, just to check your understanding of graphic models, what's properties, what is d-separation, and all kind of stuffs. Again, it gave you 2 weeks, so please start doing that, and no hurries. Okay. By the way, so if you haven't started wrapping up your midterm project report, please start right now, because Friday we expect to see your current status of your project. Okay. So in the last lecture, that is right before our spring break, we actually talked about another important component in probabilistic learning. That is, how do we learn, right? So we've introduced like several families of probabilistic models, like graphic models, like Bayesian networks, like generalized linear models. They kind of like very expressive, very powerful, very general. You can leverage them to model the data you have observed, right? And model their relationships, encode your prior knowledge or experience or beliefs, whatever. Right? But once your model is there, right? Once you have collected data, another important thing is how do you estimate your model? Right? How do you train your model? How do you make your learn the model parameters or posterior distributions? How do you leverage those learning results to make predictions, right? Either you conduct predictive distribution or you calculate point prediction, whatever, right? So these are, in general, can be categorized as learning procedure or inference or training. Like there are many synonymous, but they're referring the same thing. But in general, given the model and data, how do we perform necessary computation, right, for our required task, either prediction or analysis and so on, right? So to resolve that problem, we need to look at a bunch of algorithms. As we mentioned before, right? One critical challenge in probabilistic learning is the computation, right? Because in Bayesian world, we're mostly interested in calculating the posterior distribution. However, according to Bayes' rule, if you want to compute them, you have to calculate the marginal distribution of the data, right? Which is also called model evidence. And because this integral is really high dimensional, doesn't have closed form, it's very hard to compute. So there's a funny thing about probabilistic modeling. People outside this area often mock this area that, like, okay, you have a perfect tools to construct all kinds of models, right? It's elegant, they're fancy, but you don't have a way to find the right answer. It's very hard to compute, right? Except a few like special cases which we have covered, like Bayesian linear regression models or Gaussian mixture models, which we're going to discuss in the next step. You might be able to compute the posterior distribution in a closed form, but in most cases, 99.9 plus 99.9999, whatever, those cases are the posterior distribution is infeasible to compute. You'll never be able to get exact posterior distribution. So that means in practice, well, we always have to find kind of approximation. You have to develop some kind of economic way to find out some reasonable approximation. So that's the important part. And this is a second large topic we're going to discuss in subsequent lectures. So you see that actually how to conduct approximate inference in Bayesian learning, it's kind of like art. Right? The approximation techniques and approximation families you choose is not only dependent on the accuracy, namely how closely your approximation is gonna be from the ground truth, but also how economically, like how efficient, how effective. Right? And it's not like I only have to get a posterior kind of completely or 95% overlapping with the true posterior. It's not like that. In practice, you'll see that many quite rough approximations can work well also. So it really depends on how you're going to trade off your computational budget to the approximation quality. So in our class, we're going to introduce several fundamental strategies that can enable you such kind of trade-off. But in practice, when you develop your own algorithms, you have to make the trade-off, decide the trade-off by yourself. And you see that all the state of art, all the cutting edge research about approximate inference are based upon those fundamental strategies. I've never seen any other methods get out of those like fundamental frameworks. Okay, so this is just a general overview to give you a sense. But in the last lecture, we have looked into perhaps the most straightforward approximate inference approach. It's called Laplace approximation. Okay? And just for you to recall, you just expand your joint probability at the map estimation, right? And use second order Taylor approximation to approximate the log joint probability. And then you do normalization, you get a Gaussian. It's pretty straightforward. But there are some problems, right? For example, if you use Laplace approximation, you always assume your posterior distribution is approximated as a Gaussian, right? What if I don't want my approximation as a Gaussian? I want my approximation to be a mixture of Gaussian or other more flexible or expressive family of posteriors. What shall we do? Right? And secondly is that, okay, you always have to calculate Hessian matrix, right? But what if you have a very high dimensional random variables, right? And your Hessian matrix will be very large. You have to seek for kind of like block diagonal approximations. So do you have like more flexible choice of the approximate form? So starting from today, we're going to introduce a family of very commonly used approximate inference approach. It's called a variational inference. So even I think the dominant technology in machine learning right now is deep learning, but many deep learning works are based on their model inferences based on the variational inference framework. And maybe someone of you have heard about variational autoencoders and so on. And they are all based on the variational inference framework. So here is outline of our variational inference topic. We're going to start with a classical inference algorithm or training algorithm, which is called EM algorithm. And we will use this so-called Gaussian mixture model. We can view it as a probabilistic version of K-means algorithm, a probabilistic version of clustering algorithm, a clustering model as an example to showcase how EM algorithm is working. So why shall we introduce EM algorithm? You see that the variational inference, the basic framework, actually is based upon the EM algorithm. The only difference is that EM algorithm assumes that, okay, at every step, you are able to compute the posterior distribution in a closed form. Of course, this is kind of like very strong requirement. In most cases, you are not able to compute posterior distribution, right? So if you are not able to compute the posterior distribution, how should we approximate, right? You see that, okay, we kind of leverage the Jensen's inequality to find that maximizing the so-called lower bound of the model evidence is equivalent to minimizing the KR divergence. So in the EM algorithm framework, you see that KR divergence can always reach 0. But in variational inference framework, the KR divergence is non-zero. That means there's always some gap. And then we'll highlight the concept called variational evidence lower bound. So this is a key component of the variational inference or key objective. All the variational inference algorithm essentially is to maximize the so-called variational evidence lower bound. And then we'll introduce a simple but commonly used approximate family, which is called mean field variational inference. So you don't assume any explicit form of the variational approximations. You just assume the posterior distribution is factorized. And then we'll talk about a second type of variational inference algorithm, which is called local variational inference. So the local variational inference is often combined with global variational inference, and it's basically that is to dispose of some kind of hard to deal with factors, joint probability. For example, some likelihood is too nonlinear, is too complicated. I want to use some trick like convex conjugate to relax the form of that factor. So in a relaxed form, you will be much easier to derive some updates of your variational posteriors. That's the idea. So, and we'll use the Bayesian logistic regression to showcase how we conduct local variational inference. And you see why the convex conjugate is so powerful and is useful, right? So previously we have done a few practices in our homeworks and to learn this idea of convex conjugate and to learn how to derive convex conjugate. So now we'll see why it's useful, how it is applied in practical variational inference algorithm, and then we'll introduce the variational EM algorithm. You can view like, okay, we put some variational approximation in the EM framework. And finally, we'll introduce variational message passing. So you can view as like a graphical illustration when you apply variational inference on a graphical model. Okay, so this is a basic outline to give you some kind of sense. Okay, we're going to start with the EM algorithm and a Gaussian mixture model. And so we start with some concrete model first. So now to begin with some abstract notations, right? We start with some concrete problems so that we know why EM algorithm is useful or why variational inference is useful. Okay, so first let us introduce the so-called Gaussian mixture model. So what is Gaussian mixture model? How many of you have heard about that? Okay, that's good. So Gaussian mixture model roughly can be viewed as a probabilistic version of the k-means clustering algorithm. But here, it kind of like encode the clustering procedure into a probabilistic sampling model, probabilistic sampling procedure. However, if you really want to know which cluster, each data point belongs to which cluster, you still need to estimate that model. You still need to calculate posterior distribution of cluster summons, those things. Right? So that means the inference of Gaussian mixture model or the training of Gaussian precise model can be viewed as running some probabilistic version of k-means algorithm. Okay, so let me give a more formal definition of the clustering problem. That is, given a set of data points and a cluster number k, right, which I believe this set of data points will be clustered into 4 groups or 5 groups, usually specify the number of clusters. Right? And then the problem is how do you group the data into the k clusters? Which subset of data points should be viewed as cluster 1? Which subset of data points should be viewed as cluster 2, and so on. Right? So naturally, we believe that points within the same cluster should be close to each other, right? and the different clusters should be separated. That's our basic understanding about clustering. So clustering is a fundamental data mining and pattern recognition task. This is something I don't need to stress on. Everyone knows that. Okay. So here we just give some application of k-means, right, using in the pictures, right. So if you're given a picture, you know, the picture consists of a bunch of pixels, right? Each pixel is represented by, if it's a color picture, it might be represented by RGB values, right? So, and naturally, if we want to cluster the pixels in this figure or in this picture, we get to know like different cluster of pixels represent different meanings, right? And also those clusters, the meaning of clusters will vary when you change the number of clusters. For example, these are original. These are original images, right? If you set k equals to 2, that means I only cluster those pixels into 2 groups. So you see that, okay, in the first image, you know, cluster 1, which are those brown points, brown pixels, are obviously some foreground of this image, and the second cluster of the pixels, which are like light blue or background. And if you set the number of cluster to be 3, you get more meaning. You get more fruitful meanings of those clusters, right? So you get those brown pixels that represent, you know, hairs of the boy, and also some nearby background to his clothes and so on. And again, and those yellow pixels are represent, you know, these rings, right? And background, which are still the third cluster. Right? If you take k equals to 10, you might find many more interesting clusters, right? And similar interesting discoveries can be found when you try a different number of k when you clustering the pixels in the second image. So now, an interesting question is that how can we model the clustering procedure in a probabilistic way, in a probabilistic framework? Our setting is still the same as the standard clustering setting. Suppose we are given big N data points, and we pre-specify the cluster number k. So in our probabilistic version of k-means, we use the following generative or sampling procedure to determine the generation of the cluster membership for this data point, and also the data point itself. So remember, whenever we build up a probabilistic model, we always need to come out some kind of a generative or sampling procedure, right? Hierarchically. Right? First, sample some latent random variables from some prior, and then given that latent random variable, you sample the next level random variables and do it again and again until you sample the observed random variables. So this is a typical example. So in our probabilistic modeling, right, to sample each data point n, we're gonna first sample the cluster membership Zn. Since we know the total number of clusters is k, so Zn is essentially a categorical variable, which is represented by the one-hot vector. Remember, one-hot vector is a vector full of field of 0 except only one element v1, right? So you can see that. So if the third element is 1, meaning that, okay, this data point comes from cluster 3, right? If the fourth element is 1, all the other elements is 0, in the end, that means this data point n comes from cluster 4, and so on. And Znk means the kth element in this one hot encoding Zn. Znk is 1 means that Xn belongs to cluster K or comes from cluster K. So in this way, we can write down the prior or the distribution that sample the cluster membership Zn from this categorical distribution, where this categorical distribution is parameterized by a probability vector pi, right? So pi k is the kth element in this probability vector. And of course, the summation of all the elements in this pi vector is 1. Right? So this is exactly what we have discussed before, right? This categorical distribution. And then, given the cluster membership, we're going to sample the data point Xn, which is essentially a vector, right? A feature vector, from a cluster specific Gaussian distribution. So basically, we assume, okay, each cluster is associated with a cluster mean and cluster covariance. So we first sample each data point from the cluster membership. Right? Given our cluster membership, we sample the particular data point from the associated Gaussian mean and Gaussian covariance, which is written in this way, right? So the conditional probability of Xn given Zn is this Gaussian distribution conditional on the corresponding cluster center and cluster covariance. Right? And here, for a convenience representation, right, because we need to consider the case that Zn indicates data point n belongs to the first cluster, second cluster, or case cluster. So we can just multiply all these cluster-specific Gaussian to the power of the Znk, right? Remember, this is just a one hot encoding, so each Znk is either 0 or 1, but there's only one Znk is 1, indicating its true membership. So in this way, we finish the generation of a particular data point Xn. So we can continue this until we use our probabilistic model to generate all the data points we have observed so far. So this is a whole probabilistic model that represents the cluster structure of the data. Any questions so far? Is everyone good with that? And here I just want to mention that this cluster covariance is not the cluster radius. It's just a soft white, right? Because if you sample a Gaussian, right? If you sample a Gaussian distribution, this is a mean, this is a variance. Variance might be come here, right? Variance just indicates how, on average, it deviates from the mean, right? It does not necessarily mean that your sample must be within the variance. Right? It could be possibly get out of the variance, standard deviation, right? But this has a smaller chance. Right? On average, the distance or the difference between your random variable and Gaussian mean is the standard deviation of the square root of the variance. Yes, exactly. Yeah. That's some point I want to bring out right now. Yeah. Okay. So now we can represent this probabilistic model with a graphical representation, right? So we use the independent sampling procedure to generate each data point. The generation is that, okay, given the probability vector, which indicates the prior membership for any data point, right? We sample the particular membership for data point n, right? Then given the sampled membership, we pick up the corresponding, the associated cluster, the associated cluster center and cluster covariance to sample the actual data point. and you just repeat, right? You just repeat this procedure, is RID, right? For big N times, that's the probabilistic model we assume how we generate these big N observations. So here, to identify this probabilistic model, we need to know first the probability vector pi, right? So based on which pi we sample the cluster membership for each data point. Okay. Second, for each particular cluster, what's the associated cluster mean and cluster covariance, which are indicated by mu1, sigma 1 to mu k, sigma k. Okay.
So you can say that at first, according to pi, we choose cluster, the Gaussian distribution, then according to that Gaussian distribution, we distribute it. And do it several times. Our model is this.
Several times what?
We have assumed that our data is produced by this procedure.
Yes.
According to pi, we choose a number, 1 to k, and then according to corresponding Gaussian distribution. Yes,
exactly. Yeah. Well, of course, someone might argue that why should I assume that given the cluster membership, the data points are sampled from a Gaussian? Well, that's a fair argument. You can assume a more other distributions like student T distribution or whatever other distribution you would like. But here, we just commonly use the Gaussian distribution. It is easier to for the inference, easier for training and prediction, and also easy for analysis. But that does not necessarily mean that you cannot use other distributions. Okay, so we know that given this observation, given the data, right, we know that the model parameters are the model itself are determined by this pi vector and also the Gaussians, cluster specified Gaussians, right? But also we are interested in what is given the data, right? Given the fact that this data are observed, we are interested in that what is the posterior distribution of cluster membership. This is something we're really interested in, which actually indicate the clustering result. So what kind of cluster membership should better fit the whole data distribution? Right? That's what the posterior distribution is supposed to tell us. So now we have our model, right? We have designed our model, which describes the generation of the data, right? So now the data is observed. We want to estimate those parameters that determine that generate the data, and also the posterior distribution of cluster membership, which reflect the structure of data. That's our goal for the inference. So that is also called learning. Right? So learning essentially is to identify the unknown parameters or posterior distribution of the latent random variable. So here we have two tasks in learning. First, identify the parameters, like including the probability vector and the Gaussians, right? And second, we want to identify the posterior distribution of those cluster memberships for each data point. And of course, someone might argue, why should I will as a point, right? Why wouldn't we assume there's pi and sigma 1 to mu k, sigma k are also random variables? Yes, you can do that. You can also assign prior over pi and assign prior over mu over sigma. You calculate, you want to infer the posterior for all those parameters and also the cluster memberships. That's totally doable. Right? But here, let us choose a more pragmatic view, like because in practice we're most of the cases we're only interested in the point estimation of those things, right? But we are very interested in this posterior distribution of the cluster membership, because this is a posterior distribution. This just tells us kind of like soft clustering result, not hard clustering result. Because each data point, given this distribution, right, I can tell you not only what's the maximum possibility this point belongs to cluster 1. I can also tell you what is other little smaller chances it belongs to other clusters. This is called soft cluster. So then our task, like learning task, would be, okay, how to identify these two things, right? So a very straightforward way, or seemingly smart way, will be just, okay, let us just first marginalize out the cluster membership Z. Because, you know, the joint probability for each data point and the cluster membership is, you know, P of Zn times P of Xn given Zn, right? And this guy is just a categorical random variable, right? So we can simply marginalize out Zn. We can get a marginal distribution of each data point. Is Zn from 1 to k, so you see that it's pi k times, you know, this guy is just a cluster specific Gaussian, right? So cluster k is just associated with mu k and sigma k, right? This is exactly the form we listed here. Okay? And then we can just do the maximum MLE estimate, right? We maximize the marginal likelihood for all the data points because those data points are generated independently. So the log joint probability will be the summation over all the data points. For each data point, the log likelihood will be log summation of this pi k and the Gaussian likelihood. And of course, to get a valid probability vector pi, you got to add additional constraints that each pi k is between 0 and 1, and the summation is 1. Right? So you might need to add some Lagrange multiplier into that. So although doing this is kind of like straightforward, it's kind of feasible, but it brings a severe problem. But anyway, suppose we are able to estimate pi, mu, and sigma in this way, right? So given this parameter, it is quite easy to compute the posterior distribution of the class membership. How can I do that?
According to pi, sample, if you compute the conditional probability just using the base.
Yes, exactly. Just use the base rule. And this is straightforward because you know that P of X and Zn, the form, right? So you want to compute P of Zn given Xn, you just divide the joint probability over P of Xn, right? So P of Xn is given here, right? It's just given here. It has a closed form, so just to divide the joint probability over this, and this should be PZn equals K, and that's it. So it's pretty straightforward. As long as you know all those parameters, pi k, mu k, and sigma k, it's easy. Right? But here we want to point out that if you simply maximize the marginal likelihood without considering the cluster membership Zn, it will bring a singularity issue. It will make the whole learning procedure very painful. It will easily give you a very unreasonable result. How does it happen? Let's look at this example. Suppose we're just clustering one-dimensional point. Right? So those are black points, and then our covariance now becomes just the variance, right? This is just a scalar. So suppose we choose k equals to 2, and you have to start with some initial cluster center and covariance, right? To learn those parameters, like how do you initialize mu n, mu 1, sigma 1 square, mu 2, sigma 2 square, right? And then you optimize it by maximizing the likelihood. And if you happen to initialize one mean, one cluster mean to be the data point, for example, just this specific data point, what will happen? Remember, we're trying to maximize the likelihood, right? So let us look at this data point. So if you look at its log marginal probability, it will be like pi1 times, let me denote this guy by x, say xn. So it's an xn given mu1 sigma 1 square plus pi2 times xn mu2 sigma 2 square, right? And mu2 happen to be xn or very close to xn. So now, if I want to increase this likelihood, sorry, if I want to, because our goal is to maximize likelihood, right? If I want to increase the likelihood, given that xn equals to mu2, this guy and this guy is the same, what shall I do to make it larger and larger? Yes, exactly, right? So if we look at a Gaussian distribution, right, we know that at the mean, it achieves the largest density, right, or log density, right? So if you make your variance smaller and smaller, the density at, or log density at the mean will become larger and larger, right? In the limit, if you take the variance to be 0, it can become a delta function, right? So that means the density becomes infinite. So similar thing is happening here, right? If your mu2 is very close to xn, is xn itself or very close to xn, in order to maximize the likelihood, I'm going to have a tendency that make sigma 2 getting closer and closer to 0. And in the end, what will happen is that, okay, your cluster, the second cluster will collapse to this particular single point. Okay? That's called singularity. And all the other data points belong to another cluster. Mathematically speaking, this is not wrong. It gives you some kind of maximum value of your log likelihood, but practice is not reasonable at all. If you're doing cluster, you don't want to have a cluster of a single point, and all the other points belong to other clusters. This is not something you want. Right? You want your cluster can reflect the structure inside data, right? Some close data points or should be grouped together. Other close points should be grouped together. You don't want this particular point forms one cluster, right? All the other points follows to form other clusters. So this is not reason. That's the reason why when we learn Gaussian mixture models, we usually do not marginalize out the latent cluster membership variables, because it is easy to get singularity issues. Even at the beginning, you don't initialize your cluster mean to overlap some particular data point. But as long as during the optimization procedure, you kind of like moving around those mean, right? As long as happen to move too close to some data point, there's a tendency that it pushed toward that data point and until it overlap, and then collapse your cluster variance to be very close to 0. So that's the issue. So the question is, how can we avoid this problem? To avoid this problem, I mean, a straightforward strategy is that, okay, let's try to consider the cluster membership jointly, right? Not just marginalized out, because the problem is caused by marginalized out the cluster memberships. Now, let us just jointly consider the cluster membership variables for each data point, and also those parameters, like the probability vectors and the cluster mean and cluster covariances. Right? So now our goal to sidestep that problem, the singularity issue, we want to jointly estimate the model parameters and the posterior distribution of the cluster membership of each data point. So how can we jointly estimate? How can we jointly estimate them? Right? So we're going to use the so-called EM algorithm. So what is EM algorithm? So let us first put aside that Gaussian mixture model. We have a general case. Suppose we have some model, right, governed by some parameter theta, which are only interested in point estimation. We do not consider it as a variable. Just assume it's some points we want to estimate. Just like the cluster mean and cluster covariance in the Gaussian mixture model. Right? In a given theta, we sample the latent random variable z. Here, z, we do not want to treat it as points. We want to get some posterior distribution of z given x. Right? And then given z, you will sample x. Right? This is your hierarchical graphing model. Right? And then your marginal distribution of the observed random variable x given theta, which is also referred to as a model evidence, right, is actually the integral of the joint probability with respect to z. This is just marginalization. And of course, theta here in Gaussian mixture model corresponds to the probability vector pi and also the cluster specific mean and the covariance matrices. Right? And z will be in a Gaussian mixture model corresponds to the cluster memberships. So an important insight from this log marginal probability is as follows, and is also the foundation based upon we develop EM algorithm and also the variational inference algorithm. So what's that? If you look at the log model evidence, which is log marginal probability of the observation x given theta. So according to the definition, we know that inside this log, this should be an integral, right? Marginalization over the joint distribution of x and z given theta. Now, let us introduce a distribution of z. And the z can be any distribution. Like, for example, z here, we just assume z is continuous, for example. Right? You can assign any Gaussian distribution with z or any other continuous distribution you like. Right? And of course, you're assuming this Q of z is not zero in support in the domain. Right? So you can divide your joint probability by z and times z. Right? It doesn't change the result at all because QZ and QZ here is just to cancel in a numerator and denominator. Right? So next, the funny thing, the interesting will be, okay, let us apply Jensen's inequality here. So you will this guy as some function of z, right? And this guy is a distribution of z. And according to Jensen's inequality, you can immediately derive a lower bound where you put the integral outside and put log inside over this fraction in my parentheses. It's called Jensen's inequality. So in this way, you get a lower bound of your log model evidence. Does it make sense? It's just the application of Jensen's inequality. And for any function like logarithm of expectation of some function, it is just no less than the expectation of log of that function. This is called Jensen's inequality, and it is derived from the convex. It's actually concave property of the log function. So this is a lower bound, and this is our model evidence. Right? So now, if we want to look at the gap between this lower bound and the model evidence, we'll see that this gap is actually the KL divergence between your introduced distribution over z and the posterior distribution of z given x. So we can just check, right? So this is a logarithm of your marginal probability of data, which is log mod evidence. So this is the lower bound we just derived from the Jensen's inequality, right? And so this is a KL divergence. The KL divergence from its definition is just the integral of QZ logarithm fraction of QZ over P of Z given X, right? This is by definition, right? You can try to add the two terms together. Right? You know, they are all integral with respect to Z, right? So you just merge the two log terms. So essentially it's a log P of X Z given theta over Q of Z plus logarithm Q of Z given P of Z given X, right? Inside the integral. If you just merge them together, so this guy summation of two logs is just the log of the product. Right? So just multiply the terms in the log, you cancel this out. So the joint over the posterior, which is P of X. P of X has nothing to do with Z, so that means your integral over Q of Z. You can move P of X outside. Right? Also, it's a log P of X. You can move log P of X outside and integral over Q of Z is simply 1. It'll give you this log mod evidence. Oh. Sorry. Does it make sense? Okay. I mean, although deriving is a structure, right? The log mod evidence essentially is a summation of its lower bound and plus KL divergence. Really simple. It's just a one-step application of Jensen's inequality. But this structure is very, very useful. It's actually fundamental to most of the approximate inference algorithm. So now, let us leverage this structure to develop the EM algorithm first. Right? So we can view the lower bound of the model evidence as a function of theta, and also a distribution function of Z. Right? So this distribution function, of course, can be some Gaussian distribution with mean 0 and variance 1, whatever. Right? So it's actually a function of two terms. One is the theta model parameters. The other is some kind of arbitrary distribution. And because the KL divergence is always non-negative, right? It's a property of KL divergence. That means this lower bound is always a lower bound. The log mod evidence is always bigger than or equal to this L function. And we achieve equality only when our Q of Z is the same as the posterior of Z given X and theta. In that case, when Q of Z equals to P of Z given X and theta, we know that KL divergence is simply 0. Right? So then the lower bound becomes identical to the log mod evidence. So namely, the log for any theta, for any model parameter theta, the log mod evidence will equal to L theta and Q star Z, while Q star Z takes the posterior distribution of Z given X and theta. Right? So this structure allows us to maximize the lower bound to improve the model evidence, because our goal is to estimate the model parameter theta. Right? We want to maximize, we want to iteratively increase this log model evidence to learn our model. Right? And suppose we can find some theta value which makes this model evidence to be maximum. We have learned the parameters. We rule that kind of parameters as our best parameters. Right? That's our goal. So now, to maximize model evidence, I mean, instead directly maximize this, right? We can try to maximize the lower bound first. Given the current theta, right? So we know that when your Q takes the true posterior, your lower bound will be exactly the same as the model evidence given the current theta, right? So now let us fix this Q star Z. And we will see that as free parameters. And we maximize this lower bound with respect to theta only. So can you imagine that we get a new theta, which is called theta nu, with the old QZ, right, which is Q star Z. And we know that this lower bound, this L, taken the value of theta nu will be bigger than this L taken theta. Oops, what happens? Okay. And again, because in all the cases, this lower bound will be less than or equal to the log model evidence on the theta nu. So you can see that this theta nu actually increase the log model evidence, right? But we never need to explicitly maximize log model evidence itself. We just need to maximize the lower bound. Does it make sense? That's the key idea. So that's the key idea of the EM algorithm. So essentially, it leverages the lower bound of the log model evidence as a bridge. So as an intermediate result, and you maximize the lower bound with respect to theta only. You get an updated version of your theta, and this updated version of theta guarantees to increase the log model evidence. Any questions so far? This is a very smart idea, but in general, this is called a majorization maximization framework. I mean, if you take some, if I'm taken some optimization class before, in general, this framework, like you're building kind of like a surrogate function to the objective function. You maximize surrogate and to iteratively improve the parameters of the original objective function. This framework is called majorization maximization framework. But EM is one instance of such kind of optimization approach. Okay, so now we can look at the algorithm framework of EM algorithm. So basically, it's very simple. We just alternatively doing two steps. One is called estop. At current parameters, model parameter theta old, we first need to calculate the posterior distribution of the latent random variable z, given the current model parameters and also x. Because only when Q of z taken that, your lower bound will equal to the true model evidence given the current parameters, right? And next, we're gonna fix Q of z. Like for example, after evaluating Q of z, you got this is a Gaussian distribution, which is with mean to be 0, 1, and variance to be 0.5, 0.6. For example, I just give a random example. You just fix it, right? And this guy is ruled as a fix to theta. You just will theta in your model evidence lower bound as some free parameters. You maximize L with respect to theta. You get a new version of theta. This is called M step. Right? And through our previous analysis, we know that the model evidence at theta nu will be bigger than or equal to the model evidence at theta O. Then we finished one update. We proceed to the next iteration, you calculate the posterior under the current theta, and then plug in into your lower bound and fix that posterior, that is QZ, right? Maximize the theta again, you get update of QZ, you again improve the log model evidence. You keep doing that until convergence or you reach the maximum number of iterations. This is called YAM algorithm. So this whole algorithm can be, illustrated in this, this graph, right? So at the current parameter theta O, right? When you calculate the posterior distribution on the theta O, you make it as a Q of Z, right? You fix it, right? And then you only maximize theta here with respect to L, right? With this guy fixed, you get a new theta, right? Which is called theta nu. Well, we know that your lower bound evaluated at theta nu and O posterior will always be better than your L evaluated at theta O and O posterior. And this guy is upper bounded by the model evidence on the theta nu. So in this case, you can see that you always improve the marginal log model evidence.
So yeah, by coordinate extent and the lower.
Yes, yes, exactly. You can view it as a coordinate extent or whatever, yeah. That's another good way to understand that. If you, this is essentially to tell, okay, you want to maximize this guy, right? If you fix theta, you maximize Q of Z. It's actually, you're maximizing objective function with respect to a functional. It's a function, it's not some parameters. And this Q of Z will give you the posterior distribution. Okay? And also, when Q of Z becomes optimal, it reaches the log model evidence. And then you fix that, you maximize L with theta. So yeah, but I usually don't explain that in that way because you have to be clear that when you maximize L with the Q of zeta, you're essentially doing functional maximization, not just quantization. Another question? Does it make sense to everyone? Okay, that's great. That's really great because this is something from my past experience, people often feel a little bit confused. But once you get over this, well, all the other things like variational inference, all the framework is pretty straightforward. It's pretty straightforward extension along this algorithm. Okay, so now we apply this framework to train our Gaussian mixture model. So this again is our Gaussian mixture model. To sample each data point, we're going to first sample the cluster membership Zn from the categorical distribution. Then given Zn, we sample Xn from the cluster specific Gaussian. So here, our model parameter theta consists of the cluster specific mean and cluster specific covariance, and also the probability factor. That is the prior probability a data point belongs to each cluster. So first come to the estop. Suppose we have already get our theta, right? So we know that when we set the Q of Z to be the posterior of the data points, given the current model parameters, it will make your lower bound reach or arrive at the true model evidence. Right? And we have shown that the posterior probability that each data point n belongs to K is essentially this form, right? That is given the model parameters, how do we compute P of Z and given Xn, right? So you can just leverage the base rule. This is straightforward, P of Xn, and numerator comes here and denominator comes here. It's pretty straightforward. And then we can substitute our Q of Z, right, which is computed here, which is actually the posterior distribution of the current posterior distribution of Zn given the current model parameters. We just substitute into our lower bound. Remember, the lower bound is essentially a expectation or integral of the Q of Z and logarithm of this fraction, right, which is the joint probability over the Q of Z. And here, because our Z are discrete random variables, so the integral becomes summation. So, and when we take out of this Q of Z, right, so you know log fraction is log minus log, right? So Q of Z, log Q of Z, this guy has nothing to do with the parameters we want to estimate. It's nothing to do with mu, sigma, and pi. Those things we want to estimate. So they're constant. So you can just throw out. So that means our lower bound can be viewed as the expectation of a log joint probability on the Q of Z plus some constant. And you can further calculate logarithm of the joint probability. Right? This is our joint probability. It's just the product over the data points and product over each category and pi k to the power of z and k, and also the Gaussian distribution of the xn under mu k and sigma k to the power of z and k. Right? If you take the logarithm, it's just straightforward. Right? It's just you just move z and k in front of log, right? And also z and k in front of this logarithm. So now you take expectation of Q of Z, right? So remember, pi k, mu k, and sigma k are not random variables. They're just points. Right? The only random variables here are just z and k. Okay? You take expectation, you just move the expectation here. Okay? So you got your model evidence lower bound is just the summation over n over k, and now expectation of z and k just the posterior probability that z and k is 1, right, which is gamma and k defined here. And similarly, gamma and k here. Okay. So the remaining thing is just to maximize this guy. And maximizing that is pretty straightforward. You just take the gradient with respect to pi k, mu k, and sigma k, and everyone has done that before. And I also need to put some constraint that pi k, the summation of pi k must be 1, right? So it's relatively easy to get to the result. Like pi k nu has this form, and mu k nu and sigma k nu have the following forms. So you can see that pi k nu essentially is what? Is just the summation of every data point. The posterior probability of every data point belongs to cluster K, right? Just sum over them and then normalize it. This is your pi k nu. And similarly, if you look at mu k nu, you can see that it's just the weighted average of the each data point, but weighted by the probability each data point n belongs to cluster K. And you can find similar weighted summation structure in the cluster, in the update of cluster programs. There's some interesting structure. We will look at the updates of those parameters. But I won't be able to derive this for you. I will leave it as an exercise for you guys. So you can see that as long as at the beginning, your pi, mu, and sigma are not crazy. Right? I mean, your pi should be non-zero for every entry. Right? If you have 0 entry, it's kind of like in the beginning you assume some singularity. But if starting from the beginning you have some reasonable initialization of those pi, mu, and sigma from their updates, right? You can see that the updates of all the gamma n k and pi k, mu k, sigma k are quite smooth. So we won't be able to have any singularity issues. That means your some entry of your pi like converts to 0, and some sigma k converts to like 0. It's really it is much less likely to happen. Now let us look at some concrete example. We're running EM algorithm for GMMs, right? The Gaussian mixture model. So this is our original data, right? So visually, it should be clustered into 2 groups, right? Those green points. So these are initializations. So there's 2 cluster centers, which are quite far away from the points. Should use this guy. And cluster Y, the cluster covariance is assumed to be identity matrix, right? And the cluster and the pi is assumed to be uniform. Right? So, and these are the color on these points in the second figure here just indicate the posterior probability under the initial parameters. Each data point belongs to each cluster. You can see that the closer to each cluster mean, the larger the posterior probability that data point belongs to this cluster. And in the middle, you can see that it's kind of like a mix, meaning that the posterior cluster probability is around 0.5. But then when you run the first iterations, you calculate the E step, get the current posterior, and plug into your lower bound of the model evidence. You maximize the cluster covariance, and the pi vector. So you can see that the mean and the covariance, the cluster mean cluster covariance changes dramatically, right? And also the cluster covariance is no longer identity matrix. It becomes an ellipsis, right? That means it's not identity anymore. So you can keep running it. You can see that the cluster mean is indeed moving toward the cluster mean we believe should be. And also the cluster covariance is kind of like more and more adapt to the shape of the data points, the shape of the substructure of the data. And finally, after 20 iterations, which I believe the algorithm has already converged under some low tolerance level. So you can see that we end up with these 2 reasonable clusters. Any questions so far? Mm-hmm. Milky new. Yeah. So here, when you calculate E step, I want to emphasize again, this is very important. Don't get confused, right? You got this the gamma nk completely all from mu k old, sigma k old, those things, right? Here, you're gonna assume all those guys are constant. We optimize mu, sigma, and pi. You're not gonna change mu k old, sigma k old. They're just constant. Is there fixed there? You only change the remaining part, which does not involve any gamma k. Like here, it will be here, right? Log pi k, log normal of xn given mu k and sigma k. Those are free parameters you want to optimize. But the pi k old, mu k old, and sigma k old, which determine gamma nk here, won't be changed. They're ruled as constant, completely constant. That's the idea of the EM algorithm. Any other question? Okay, great. So I will leave 2 practice problems for you guys. Like first, try to derive EM algorithm to learn a mixture of Bernoulli distributions. So here we assume your each data point is a continuous vector, right? Feature vector. We assume it is sample from Gaussian given the cluster membership. But what if your observation is just the binary variables? Right? Xn is either 0 or 1. We can assume, okay, given the cluster membership, those Each data point is sampled from Bernoulli distribution, but parameterized by different parameters. You can still derive an EML algorithm to try to cluster 0, 1 points. And the second practice will be derive EM algorithm to learn Bayesian linear regression. So we talk about them before, right? So for Bayesian linear regression, you can assume your weight vector prior will be a Gaussian distribution. Well, let me use some diagonal Gaussian, right? Mu times V I, and then given the V vector, given the V vector and the input vector, the output is sampled from another Gaussian, right? W transpose xn and beta, right? So, of course, if you want to perform some nonlinear transformation, you might put a nonlinear transform over phi xn. It doesn't matter. So now if you want to estimate posterior of W, given the data, given all the training data, as well as those hyperparameters, which includes mu and V and beta, right? How can we do that? We can use EM algorithm. In each step, we can, given the current mu, V, and beta, to derive the posterior distribution of W, which is Gaussian. We have shown that before. Right? And then you plug in this posterior into our model evidence lower bound, which will be something like that, right? Log P of W and P of Y given X given W divided Q of W, right? You plug in Q of W, which is posterior, right? Current posterior into this lower bound. You maximize the lower bound with respect to the hyperparameters mu, V, and beta. You can update mu and V and beta. Right? And just iteratively do this, follow this framework. This is another effective way to learn the Bayesian linear regression model. Any questions so far? Okay, so it looks like everybody is happy with this EM algorithm framework. Right? So now let us switch to the variational inference framework. So we're going to still use this general model. That is okay. We assume some some hyperparameters theta. We only care about point estimation. We do not seek for posterior distribution of that. We just want to give some point estimation. Okay? Now, given theta, we first sample some latent random variable z, and given z, we sample the observed random variable x. So let us put aside this hyperparameter theta first. Let us assume we know theta. Okay? And then later we can talk about how to join the estimate theta. Our goal is just to calculate the posterior of d given x, of course, given the known theta. When we run the EM algorithm, we assume this guy, this posterior distribution of z given x under any setting theta is always easy to compute or have some closed form. However, in the general case, the posterior distribution is usually infeasible to compute. As we discussed before, right, we know that for following Bayes rule, you have to compute the marginal distribution of x. You have to marginalize out z from its joint distribution. Right? So usually it's infeasible because it's high-dimensional integral or intractable integral form, except a few cases where in the Gaussian mixture model, Bayesian linear regression model, this integral is relatively easy to derive. Right? But in most cases, you cannot get analytical results. Like even for one-dimensional random variables, for example, suppose your z is just a scalar. It's sampled from a Gaussian distribution, a standard Gaussian distribution. But given z, you sample x from this guy. This is just like this regression. You first transform z through the sigma function to get probability. Then use this probability to sample x. X is either 1 or 0. Sorry, this should be z. should be x. Yeah, x is either 1 or 0. Okay. And now, if you want to compute the posterior distribution of z given x, even it's just a scalar, is analytically intractable. You don't know the form of that. So then the question would be, okay, in that case, how do we compute the posterior of z given x? The idea of the variational inference is as follows. Since the true posterior is complicated and tricky to compute, can we find a simple form of the distribution? For example, I just assume this posterior is a Gaussian. And then we want to find a Gaussian to approximate the true posterior. Okay. In other words, can we designate a family of simple distributions, and from which we find the best member that is closest to the true posterior? Like we don't know the true posterior, right? It might be here, or in space, right? We do not know how to get to this true posterior. But let us assume we're going to approximate with some Gaussian. And this is a Gaussian family. The true posterior obviously can be outside of my approximation family. Then my task would be, okay, how do I find a particular member in my approximation family which is closest to the true posterior? And if I find this optimal one in my approximation family, my task is done. I'm going to use this guy as my approximation. So this is called variational. This is the idea of the variational inference. Okay, so we'll talk about the detail on Thursday. Okay, thanks.